So water is unbelievably diverse, powerful, and essential. You can't have great coffee without great water. You also can't have great coffee without great coffee. I'm going to let these famous explorers, which you guys will recognize, tell you another thing about water.
The universal translator is coming online, sir.
Ugly, giant bags of mostly water.
Bags of mostly water. An accurate description of humans, sir.
That's true. You and I are, in fact, mostly water. By mass, something like 60%. If you count the molecules, it's actually closer to 99%. Water controls our weather. It has shaped many of the landscapes on Earth, including the Great Lakes just down the road. It has dictated the rise and fall of many of history's great civilizations. The ancient pharaohs derived a lot of their power because of their knowledge of the Nile River and its annual flooding, which distributed fertile silt over the valley and allowed them to grow food and feed their population. Those pharaohs fought wars against the civilizations in the areas of what are now places like Kenya and Ethiopia, because that's where the headwaters of the Nile were coming from, and they recognized the importance of having control over the full source of water. The ancient Romans were some of the great water engineers of history. They created the aqueducts, which probably all of you are familiar with, like what's pictured there. Those aqueducts allowed the citizens in Rome, in ancient Rome, to have a per capita water use that rivals approximately what we have today in the United States. Truly phenomenal considering when that happened. They also came up with all other kinds of interesting ideas with water. They came up with water mining. They had what we call fit-for-use water, where they had different streams of water for different purposes, some more pure than others. So their public fountains would have dirtier water than going into their baths, for example. This is an idea that we've gotten away from and actually are just now starting to come back to again. The ancient Chinese civilization, that whole region was unified in part because of the development of the Grand Canal, still the largest canal on Earth, which merges the Yangtze and Yellow Rivers and allowed the movement of grain to feed their armies. One of the recurring lessons that we learn from history is that civilizations that rely for too long on old water technologies are overtaken by those societies or civilizations that innovate to take advantage of water's opportunities. Another interesting historical note is that if you look at Europe as an example, there's no major inland river system running through Europe. There's no Indus and Ganges or Nile or Yellow or Yangtze and so on. And historians will tell you that's one of the reasons that Europe developed into small independent nations instead of one large empire. And that, then, those small independent nations gave rise to liberal democracy as we know it today. So in a sense, you can connect that back to water. Now, water technology specifically has driven a number of revolutions in history. So if you go back to the origin of transoceanic sailing, that is what globalized civilization in the first place. Water wheels launched the Industrial Revolution. Watt's steam engine revolutionized both transportation and industry. Water sanitation extended human lifespans in a leap that probably has never been rivaled before or since. Great dams, like Hoover Dam that's pictured here, for the first time gave us some level of control over Mother Nature's fickle precipitation, limiting both flooding and droughts to some extent. That multiplied food production. That is one of the reasons that the United States rose to power in the last century. They also, of course, provide electricity. There are now over 40,000 of these things around the world. Essentially everywhere you can build a large dam, just about, there is one now. And even a more recent example associated with water would be intermodal shipping containers, like those pictured here. Actually, 90% of global commerce happens on the water. So we use water for a lot of different things. Do you guys know what the largest single withdrawer of water is in the United States? Any guesses? Agriculture is the largest user of water. I chose my words carefully here. Withdrawer. I'll explain the difference in a moment. So agriculture uses water because they take water from a source and use it to irrigate, and then that water is not immediately useful for anybody else. It's going to evaporate from those crops and enter the water cycle through some other path. The largest single withdrawer of water in the United States is power plants, by far. It's over 200 billion gallons a day go through thermoelectric power plants. They're usually sited. This is coal-fired power plants, nuclear power plants, natural gas. They all work basically the same way. They're sitting next to a lake or river. They have an intake of that water. They heat it up using burning coal or nuclear heat or wherever their heat is coming from to make steam, to turn turbines and make electricity. And then a little bit of the water is lost through that steam, but most of it is returned to the body of water from which it came. That water is also used for cooling in the power plant. So it's massive, massive amounts of water, and this represents a big chunk of what is called the energy-water or water-energy nexus. There are all kinds of ways in which water and energy are intimately connected to one another. One is that we use massive amounts of water to make our energy. The flip side of that is also true. If you look at where our electricity goes that we generate with those power plants, the largest single user of that electricity is the water treatment, distribution, processing, use system. So those are the two biggest pieces of the water-energy nexus, but there are many ways in which water and energy are connected beyond that. If you're interested in this, you can actually find this report online. It came out in 2014 from the Department of Energy called the Water-Energy Nexus, where they review all the different myriad ways in which these two spheres are connected to one another. So water's all over the place. But I'm going to spend a little time trying to convince you that, in a sense, water is actually invisible. In fact, it's hidden all around us, even in this room. So here's what I mean by that. If you take 683 gallons of water, that would allow you to grow, speaking of agriculture, 6 pounds of alfalfa hay. Now, if you take those 6 pounds of alfalfa hay and you put them into a machine that looks like that, it will give you 1 gallon of milk. So it's just 1 little gallon of milk, but it represents nearly 700 gallons of water. The name for this is virtual water or embodied water. And it's not just milk. It's in all of our food. 1 grape, not a bunch of grapes, but 1 single grape represents about 1/3 of a gallon. A single walnut, something like 5. A single potato, nearly 7 gallons. A cup of coffee, not a venti latte from Starbucks, but just a cup of coffee, is almost 40 gallons of water. If it is a latte, you're using dairy. As I just described, dairy is very water intensive. For example, a single Greek yogurt is almost 100 gallons of water. And the real culprit when it comes to use of water for food would be meat, especially beef. 1 hamburger is well over 600 gallons of water. But it's not just food. It's things, too. It takes water to make stuff. To make steel, you need water. To make 1 pound of steel, pretty small piece of steel, it's something like 11 gallons of water. You can do the math also for all the raw materials we use, plastic, cement, cotton, paper, you name it, they all take water to manufacture. What that means is the clothes that you're wearing, the phone that's in your pocket, the car you drove to get here, all of those things represent massive amounts of virtual water. Now, one of the things about water is that you can't move water on a massive scale from one place to another, not too far geographically separated. And I'll get to that a little bit later, why we don't do that. But you do move things around the world on a global scale. All these goods that I just described, food and cars and electronics and everything else, get moved all around the world all the time, of course. And so when you're doing that, in effect, you are moving water, virtual water, around the world. And there are folks who have looked at this and kind of calculated, sorted out that some countries are net exporters of virtual water and some are net importers of virtual water. And some of these things are probably not that surprising. Regions like North Africa and the Middle East, very dry, are net importers of virtual water. In this case, the bulk of that would be food because they just don't have enough water to grow the food they need in that region. You can see the United States is a net exporter of virtual water. Let me give you one example connecting those two regions. There's a company. It's a Saudi Arabian company called Al Marai. I don't speak Arabic, but I'm told that Al Marai means the pasture. And the pasture that's being referred to there is not in Saudi Arabia, it's in the southwest of the United States. And what Almarai has, it's by the way the largest vertically integrated dairy company in the world. They are growing alfalfa hay in the American Southwest, and the water that's being used to grow that hay is groundwater. We'll get to groundwater in a bit. So they're extracting groundwater, growing alfalfa hay, and then shipping that hay to feed cattle in Saudi Arabia to make dairy for their use. What that means is there are massive amounts of virtual water moving from one very dry region, the American Southwest, to another very dry region, Saudi Arabia. And to the best of my knowledge, there is no international regulation of this movement of virtual water, despite the fact that it has massive impacts on our water resources all around the world. And so I believe this is something that the international community needs to take a much closer look at. Are we using our limited water resources in the most intelligent way? So water is very important, but it's actually becoming more important as we go forward in time. And let me explain why that is. So we are lucky on Earth to have a lot of water, a ridiculous amount of water. So our oceans have 352 quintillion gallons, give or take. Now, of course, the problem with the oceans is that that's seawater, salty water, and that's not useful for much of anything other than the stuff that lives there. And that water represents about 97% of the water on Earth. So almost all of it is in the oceans. So that only leaves about 3% of the water on Earth. So let's look at that 3%. And to be rigorous here, since you guys are technical folks, part of this 3% is also salt water, just not in the oceans. So there's saline groundwater and things like that too, but we'll just ignore that part for now. So we're talking about 3% of the water on Earth. How is it distributed? Well, there's the water that we see in lakes and rivers like Lake Michigan. It looks like a lot of water. That's what I'll call renewable runoff. That's the stuff that comes down as rain and snow, and it flows down gravitationally, ultimately ending up back in the oceans, of course. Now, some of that renewable runoff percolates down into the ground through the soil and rocks, and that forms groundwater, or aquifers. And some of these are renewable. I put renewable in quotes because it's only truly renewable or sustainable if you're withdrawing the water from that source at a slower pace than it's being naturally replenished. And I can tell you that in most cases when we tap into these groundwater sources, we're withdrawing the water much faster than it's being replenished, so they are not, in fact, renewable or sustainable. There are other aquifers under the ground that some people call fossil water. This is akin to fossil fuels, not that they are made of fossilized organisms like fossil fuels are, but because they've been there for a very, very long time and are not being replenished at any appreciable rate. So some of these aquifers have been there for over 1 million years. And we are tapping some of those too to use for our daily needs. One example would be the country of Libya built something called the Great Man-Made River, tapping into fossil water under the Sahara Desert. And they spent something like $32 billion to build the Great Man-Made River. And it is projected to only last for about 20 years, because at that point, that aquifer will be exhausted. So how is this 3% of fresh water distributed? Only 0.3% of the 3% is that water that we see on the surface, which looks like so much water in lakes and rivers and so on. About 30% of it is down in those aquifers in the groundwater. And you can do the math. That doesn't add up to 100. Where is the rest of the fresh water? It's locked up in places where we can't get at it. Places like the permafrost and glaciers and ice caps. So all these things we need water for, almost all of that we need fresh water for, and it's really a pretty small fraction of the water on Earth that is usable for all those different things. There are other supply challenges, though. We have a warming planet, thanks to our use of energy. One of the consequences of a warming planet is melting glaciers. All over the planet, very well documented that glaciers are melting. And you might say, who cares if you're not a hiker who enjoys hiking in glacial mountains? Well, one of the reasons you might care is that places like the Tibetan plateau in the Himalayas, the meltwater off of those glaciers is the source of most of the major river systems that run through Asia, a few of which I've listed here. Those rivers are the fresh water source for something like 1.5 billion people on Earth and growing, soon to be 2 billion. So as these things go away, that meltwater becomes a trickle, those rivers go away, where do those 1.5 or 2 billion people get their water? I don't know. There's another challenge with water and global warming, which is droughts. So droughts are very clearly becoming more severe than they have ever been. We're familiar with the drought that's in California now that's been going on for 4 or 5 years and the effects that has on agriculture. The drought that's in the Middle East now is, there was an article in Science just a few months back that reported that was the worst drought in the region in 900 years, most likely because of a changing climate. Now, when you have water shortages like that, that leads to all kinds of problems. It leads to food shortages, for example, which leads to civil unrest. And in fact, it is food shortages in North Africa and the Middle East that was one of the major contributing factors to things like the Arab Spring and other unrest in that region. In fact, the conflict in Syria has also been tied in part to food shortages. So you can see where these supply problems with water start to become more and more serious. So we've got a small supply of fresh water, and it's shrinking. What about demand? What about the other side of the equation? Well, it's bad news there too. It's projected that global demand for water by the year 2050 will be 55% higher than it is today, in part because of a growing population and in part because of development. As I told you, you need water for everything, so if you have a developing economy, it's going to consume more water. So we've got a diminishing supply and a skyrocketing demand of surely the most important material on Earth. What does that mean? It means that in the same way that oil conflicts shaped our previous century, it will be water conflicts that are going to shape the geopolitical order of this century, especially as we move further into the century. And this is not just something about the future. Some of these things are happening today. You can look around the world, places like Central Asia, the Aral Sea is drying up. It's all but gone. So those Central Asian countries that relied on that water for agriculture are now bickering over the limited amount of water that's left. It hasn't erupted into a major, violent conflict yet, but it frankly probably will. Places like southern India, very dry. There have been folks fighting over the water resources down there for some time. You look at Bolivia and Chile, the Salala River that runs from Bolivia into Chile. The Bolivians need that water for their own needs. The Chileans need that water because if that water flows into the Atacama Desert, which is one of the driest places on Earth, massive mining industry there, which is the foundation of the Chilean economy. They need the water to do the mining. The Bolivians need the water too. There's already conflict brewing there as well. You can look in the Nile Basin, which, as I mentioned at the beginning, has been, water has been the foundation of civilization in that region since basically the dawn of human civilization. And that will become true even more so going forward as countries like Egypt rely so much on that Nile water. They're now building some dams up in the headwater regions, which are going to limit the flow coming down that Nile River. I expect that is going to lead to some significant problems. And everyone's familiar with the Israeli-Palestinian conflict, but a lot of people don't realize that part of that conflict is based around water as well. So there are obviously limited water resources in that region. And if you look at the draft peace agreements that have been written up at various times, a big chunk of that paper is devoted specifically to water. So water is surely the most important material in the world. And as I told you, water, in a sense, is invisible, which is not good for us or for water. Now, one of the reasons that water is so invisible to us is that we've been living in what I call the golden age of water. And what I mean by the golden age of water is that you have three things all at the same time with water. It is abundant, cheap, and safe, all at the same time, which is what we have in, for example, the United States, and have had that for a long time. When you have all of those things, abundant, cheap, and safe, you start taking water for granted. You lead to situations like this. So if you stayed at a Four Points hotel a few years back, the little bottles of water that came in your hotel room would have a placard on them that said this: it's water, of course it's free. What they were doing was poking fun at the hotels that charge you ridiculous amounts of money for a bottle of water. But what they're really doing there is they're tapping into something primal about our relationship with water. We feel like water should be free. There's plenty of it out there. We need it. Why are we paying for this stuff? It leads to waste. You have one pipe of water coming into your home or your apartment. You use that water for everything, from drinking to bathing to laundry to watering your plants and everything else. That water is drinking water quality. What that means is when you flush the toilet, you're flushing fresh drinking water down the toilet, which makes no sense at all. In America alone, it's almost 6 billion gallons a day of fresh drinking water being flushed down the toilet. Remember, I mentioned the ancient Romans had this idea of different streams of water for different purposes. We're just starting to get back to that again today. There are parts of the world, not yet in most parts of the United States, where they're putting in pipes where there's potable water and non-potable water. And so you have two systems in your home, some of which need to be potable and some which don't. Now, we have this system, huge infrastructure here and in most of the developed world, to clean up water, get it to us, and then clean it up after we're done using it. It is a massive, massive system that is enormously underfunded in terms of maintenance. It is estimated to be something like $1 trillion problem in the United States alone to fix up that infrastructure. To show you how much our priorities are messed up with this, we are actually spending about as much on bottled water as we are maintaining that entire system of water infrastructure. That makes no sense. So what that means is that the system is falling apart, and a lot of it is invisible to us because it's under the ground. You don't see the water mains. But take the city of Chicago, a lot of those water mains were put in 100 years ago, and they are past due to be replaced, and they're failing all over the place. And it's not just Chicago. There are leaks all over the place in water mains, all over the country, all over the world. And what that means is we spend a lot of energy, resources, to clean up water, to make it drinkable, and we pump it into those water mains, and then we actually lose 1 in 6 gallons that just leaks right out, invisible to your eyes because it's all happening underground. Enormously wasteful. Another way in which we're abusing water is this. This is not so much true in the United States, but in most of the rest of the world, sewage just gets discharged untreated back into waterways. Something like 80% of sewage worldwide is being discharged untreated, which leads to untold proliferation of disease and other problems, as I'll get to in a moment. So this golden age of water, when it's cheap and abundant and safe, is ending. In most parts of the world, you'll probably be able to get 2 of the 3, but rarely will you be able to get all 3 at the same time anymore. That will lead to water crises, and again, we're not just talking about the future. Water crisis is already part of daily life in many parts of the world. I find this statistic to be the most shocking of all in the world of water, which is that every 90 seconds, it's not a lot of time, a child dies because of a water-related disease. That adds up to thousands of children a day, every day. And that's happening because that water is tainted with pathogens. Another way in which we have a water crisis is that in parts of the world like India and large sections of Africa, people do not have water coming into their homes. They have to go get the water that they're going to use every day in their homes for everything: cooking, cleaning, bathing, drinking, all of it. All the water you use every day, it's a lot of water. They got to go get it and carry it back, walking often more than a mile one way. And the people who have to go and get that are disproportionately girls. So they spend hours every day going and fetching water and carrying it back. In many cases, that means they don't get to go to school. They don't ever get to enter the workforce and participate in the economy like their male siblings. This is a social phenomenon that I think we can move past now that it's 2016. Now, you may have heard the expression that all politics is local. I like to say all water is local. I mentioned earlier that you cannot move massive amounts of water massive distances. And when you look around the world, water scarcity is not uniform. There are regions where it's much more scarce than others. We are very fortunate here, living near the Great Lakes, to have access to one of the largest sources of fresh water on the planet. But that's a rare situation. And because all water is local, if we conserve water here in Chicagoland, that doesn't really have any direct impact on a place that is water needy, like, say, Haiti. Even if, take a country, whatever, Haiti, India, anywhere that needs more water, even if they wanted to buy water from a water-rich region, it's really just not feasible to get all the water from here to there. So why not? Why don't we have water pipelines. We do have oil pipelines, like the one pictured there, right? So we can move fluid over pretty large distances. So there are really two reasons that this doesn't happen. One is the volumes involved. We use a lot more water than we use oil. To give you an example, the Jardine water plant in downtown Chicago can process over 1 billion gallons of water a day. That's more than all of the petroleum we use in the entire United States every day. So the volumes are just massive. You wouldn't have a pipeline like that. You'd have, 100 or 1,000 of them lined up next to each other if you really tried to move a relevant amount of water some distance. The other challenge is this. How much is water worth? Well, first of all, it depends what you're going to use that water for. The pricing of water is actually quite a mysterious subject. But you can do some math and sort of back out, well, how much value was produced by the water. If you're using it to grow food, depends what crop you're growing, but it works out to be something like $20 to $100 per acre foot of water. Acre foot might not be a unit that you're familiar with. That is the amount of a liquid that would cover 1 acre of land 1 foot deep, which equates to over 300,000 gallons of water. So that also gives you a sense for the scale of water that we don't talk about gallons. Usually we talk about things like acre feet. So 1 acre foot of water, it's a lot of water. If you use it for agriculture, it's only worth a few tens of dollars. If you use it in a municipal setting, it might be worth something in the neighborhood of $1,000. Let's compare that to something we do build pipelines for, like oil. Unless you're good at arithmetic, you might not be able to do the math in your head how much an acre foot of oil is worth. It works out to be about that much, something like $500,000. I made this slide before the recent drop in oil prices, so it's probably 250, 300,000, but you get the picture. It is way more valuable per unit volume than that one, and so the energy that it takes to move those things makes a lot more economic sense here than it does here. So water is not very expensive, but it is very valuable. And I love this quote from Ben Franklin. He said, "When the well is dry, we learn the worth of water." Things like oil are substitutable. We can get our energy from other places. There is no substitute for water. There's only one water. Okay, so let's get to a little bit of science. What is water? What's the chemical formula for water? H2O. Everybody knows. Every audience I ever talk to, they can answer that question. It's the one molecule everyone knows. 2 hydrogens, 1 oxygen. What some people don't realize is that it's actually not so simple. This molecule has a bent shape to it, with both hydrogens sitting on the same side of the molecule. And that bent shape is really important because the hydrogen atoms don't like electrons as much as the oxygen atom does. And what that means is the electron cloud around this molecule is not isotropic. You have more charge on one side of the molecule than on the other side. That's called polarity. The molecule has polarity. And the polarity of water, that one feature of water that it is quite polar, controls all kinds of very important properties of water. It's what gives it, the high surface tension. It's what gives it an unexpectedly high boiling point. All kinds of things result from that. Let me give you some other examples, though. One is that polarity is what allows microwave ovens to work. Those microwaves cause polar molecules like water to vibrate and rotate, which is what heats up your food. More importantly, it is water's polarity that drives protein folding. Proteins have charges all over them. They need to fold up into very specific shapes to have the function that they have. And without water sitting around screening those charges in just the right way, they would never fold up the way they do. Without water being polar, you wouldn't have proteins. Water's polarity also leads to this very unusual material property that solid water is less dense than liquid water. There's really just a small handful of materials where that's true that we know of among all the millions of materials that we know. Typically, the solid's going to be more dense. What that means is that ice floats in water, like the ice cubes in your glass, or like the ice on the top of Lake Michigan in the winter here. That is critical for life to exist, because in the winter, water starts to freeze in cold climates, and that ice floats up to the top, and it forms an insulating barrier, which prevents the entire lake from freezing from top to bottom, and thereby killing whatever lives in the water, and so therefore life could flourish in cold climates. Another important aspect of water's polarity is that it makes it an unbelievably good solvent. It is sometimes called the universal solvent. What that means is you can dissolve all kinds of different things in water, a massive array of things. Shown in the background there is part of the metabolism that happens inside us. In our cells, in our bodies, is water, and dissolved in that water are many thousands, probably millions of different chemicals, all of them dissolved in water, one solvent. Now there's a flip side to this. Not only does it allow you to dissolve all the things you want to dissolve, not all, but many, it also dissolves all kinds of things you would rather it not dissolve. It turns out that this is what makes water so easy to pollute. Almost anything you put in the water by accident is going to stay in the water. So everything from radionuclides, heavy metals, disinfectants, all of these things stay in the water and cause all kinds of problems. Now, that's a lot of bad news about water. There is good news about water, too. One is that you can't use up water. I told you we have a lot of water on Earth, and it has been here for a very long time, since long before there was life on Earth. There's actually still some debate in the scientific community about exactly where all the water on Earth came from. The sort of two competing theories are extraterrestrial sources, comets and asteroids, which surely did bring some of our water early in Earth's life. And there's also a competing theory that there's so-called deep water that has come up. It was buried down in the mantle as the Earth formed, and then over time it came up to the surface through volcanic activity and other. Either way, it's been here for billions of years, and it ain't going anywhere anytime soon. So that's good. We got plenty of water. Now, that water, every one of those water molecules, just about every one of those water molecules, is therefore billions of years old, very old molecules. And they've just been going through a water cycle that whole time. They, at some point, are in the ocean, they get evaporated, they come down as rain or snow somewhere, and maybe they go down into the groundwater, whatever, and they end up at some point back in the ocean again, and it all starts over again. What that means is that every molecule of water in every glass that you pour has at some point in its life been inside an oak tree, it's been blasted out by a volcano, and it's been urinated by a dinosaur. Which is true, and sounds a little bit gross, but it actually teaches you another important thing about water, another piece of good news, which is that it doesn't matter how dirty you make that water, what you put into it, and you can put a lot of things into it, you can always get back to clean water again, with clean enough to drink, no matter what's in there. So that begs the question then, what does it mean to say that water is clean? What does clean water really mean? It turns out you don't want the water in your glass to be only water, only H2O and nothing else. That would actually be hazardous to your health to drink if you had that, because it would leach minerals out of your body. That's why they tell you not to drink distilled water from the grocery store. So you don't want ultra pure water for drinking water, but there are situations where you do need ultra pure water. Things like the semiconductor industry, where they are manufacturing the chips that go into our computers and phones and everything like that. They need some of the purest water on Earth to do that processing, and so they have some of the most sophisticated water purification plants on Earth. But you don't need ultra pure water or even drinkable water for all kinds of things. If you're gonna just run a boiler, maybe you don't want it to be like raw sewage, but it doesn't need to be drinkable quality water. So it's really about having the right water for the right purpose. Again, the ancient Romans already understood this principle. We got away from it. It's time to come back to it. So how do you clean water? This is not an exhaustive list, but here are a few examples of ways that we clean water. One of the traditional ways is doing what's called media filtration, where you basically have a big container of sand, and you put the dirty water in the top, and it percolates through the sand, and it comes out cleaner on the bottom. And there's two reasons it gets cleaned. One is the sand itself filters out the big stuff, because it just can't fit between the grains of sand. But probably the more important function is that the sand grains form a film on them, a biofilm, that gets microbes in it that chew up a lot of the pollutants that are in the water, degrade them into less harmful products, and thereby clean up the water as it works its way through that system. And this is still used today in many places, including here in the United States, to clean up water. The most common way you find in things like wastewater treatment plants and also in water purification plants is this mouthful: coagulation, flocculation, sedimentation, filtration, which is a multi-step process where you basically precipitate out the bad stuff, by mixing in other things. Under your kitchen sink, you might have a system that looks like that, a membrane filtration system. Reverse osmosis would be an example of membrane filtration. That's where you're pushing dirty water through a semi-permeable membrane, and you hope that just the clean water comes out on the other side and all the stuff you don't want gets trapped by the membrane. That's not used so much on a massive scale for water purification for you and I for our daily needs, but I would argue that on the technology side, that's where probably most of the innovation is happening today and in the future is in membrane filtration. You can distill water. That's where you boil water using heat from some source, or also low pressure can help you. And you hope that the water evaporates and the junk that's in the water stays behind, and then you recondense that water somewhere else and thereby have purified water. And also, we've talked a little bit about pathogens in water. Disinfection is a very important process to clean up water. The way we do that with our municipal supplies today is mostly with chlorine, addition of chlorine like in a swimming pool. You can also do it with ultraviolet light, which is what's pictured here, which kills all kinds of different pathogens. Now, if you want to talk about purification of water, and I mentioned to you that 97% of the water on Earth is in the seas, you might say, well, let's just take that salt water and turn it into fresh water. Do desalination, problem solved. But let me give you a sense for the prospects for desalination, which are good, but they're not going to solve all of our problems. So desalination is energy intensive. It takes a lot of energy to turn seawater into fresh water. If you do it by reverse osmosis, back in the 70s, it took a ridiculous amount of energy because the membranes they were using were not good. But they got really good at this in recent years. So the energy involved has come down by an enormous fraction. But you can calculate relatively straightforwardly from thermodynamics how much energy it takes just to take salt out of water when the concentration is like what it is in seawater, 35,000 ppm. And that theoretical limit is this dashed orange line down here. Turns out, of course, you can never reach theoretical limits in things. You want to talk about a really aggressive practical limit, it might be that green line. And you can see even back in 2008, they're almost there already. So there is no breakthrough coming in energy savings for seawater desalination. It's already just about as good as it can possibly get by the laws of thermodynamics. And by the way, these dashed lines do not represent anything having to do with using reverse osmosis. That's just the thermodynamics of separating salt from water, which tells you how good reverse osmosis is, that it, as a technology, can get very close to that. For those who want to be rigorous, these numbers are just referring to the reverse osmosis step in the desalination process. There are other steps, pre-treatment and bringing in the water and pumping it back out. All those things also take energy, so that adds on to this. Okay. So because of that massive drop in energy required to do it, the costs of desalinating water have dropped dramatically. Also, water needs are growing and supplies are dropping, and so that's leading countries to expand their desalination capacity on a pretty significant scale. Here's a plot of desalination capacity worldwide by year. And you can see we're building more and more every year, and that will continue for the foreseeable future. And it's happening in places that you'd expect, places like the Middle East, there's Saudi Arabia, North Africa, and so on. Places that really need that water badly. So they're willing to pay the price of that energy to make it. But let me give you a sense for the scale here. Check out this axis. You can see the maximum on this axis, which we have not yet reached, is 140 million cubic meters per day. 140. So I'm going to take this graph and I'm just going to squish that y-axis down. So there's that same graph, just squished down. That is our global water usage. So I don't want to say desalination isn't important. It's critical. You live in a country like Israel, you're very glad to have desalination. But when you look in terms of global water need, it's not even a drop in the bucket. Sorry for the pun. And you can grow this all you want. We're not going to get there, anytime soon. So we cannot be relying on seawater desalination to solve all of our problems. Okay, now let me bring it home a little bit more here to Chicagoland. It turns out here in Chicagoland, we've been thinking big about water and doing some, I'll call them innovative things with water on a big scale for a long time. In fact, dating back all the way to the beginnings of Chicago. If you lived in the city of Chicago in the 1800s, the street was a really gross place to step outside into. And that's because There were horses in the street producing their waste and just staying there on the street. And in fact, human waste was also being dumped out into the street. So it was a pretty nasty environment, also not a very healthy one. And Chicago had visions of being a metropolis, a modern city. And so this gentleman, Ellis Chesbrough, came around, and he decided he wanted to build a comprehensive sewer system for the city of Chicago. And at this time, no city in the United States had a comprehensive sewer system. Now, he had a problem, which is that the hydrogeology of Chicago was such that they could not just dig underneath the buildings and put in pipes. That wasn't going to be feasible. So he didn't give up. He said, I'm just going to lift up the city of Chicago and slide the pipes in underneath, which sounds insane, but it's what they did. They actually went with jacks, one building at a time, jacked up the buildings, and built the sewer system underneath, giving Chicago the first comprehensive sewer system in the United States. So that was good, because now the sewage is not in the street. It's going into those pipes. You know where those pipes emptied? Close, the river, the Chicago River. So you guys maybe read this book when you were in high school, Upton Sinclair's The Jungle, about the Chicago stockyards and the conditions then, back in around the turn of the previous century. If you go inside that book, you will find a discussion of Bubbly Creek. Bubbly Creek is one of the arms of the Chicago River. And he described Bubbly Creek as a great open sewer, 100 or 2 feet wide. This is actually a photograph from around that same time of Bubbly Creek. And there is a gentleman standing in the middle of Bubbly Creek on all of the waste that there is, to give you a sense for how dirty this was. Now, there was a problem with this, not just that the river was really disgusting, but the river emptied into the lake. And guess where we get our drinking water from? So that was bad, and people started getting really sick. So one solution might have been, well, let's dump our sewage somewhere else so it doesn't go into the lake. But no, not in Chicago. They said, let's just make the river flow the other way. And so that's what they did. They dredged and actually reversed the flow of the Chicago River. They built the Sanitary and Ship Canal, which runs down near Argonne National Laboratory still, and reversed the flow. So now that river no longer empties into Lake Michigan, the Great Lakes basin. It now empties into the Mississippi River basin since that time. So yeah, that sucked if you lived the other way down the river, but I guess they didn't have enough political power or whatever to stop that from happening. I don't know. That might be true. Yeah, well, apparently they didn't win. So, yeah. Okay. But that wasn't the end of Chicago thinking big about water. People don't realize it, and millions of people see it every year, but we have in Chicago, by far, the largest water purification plant in the world. And it is sitting right in plain sight. That is Navy Pier, most popular tourist attraction in the state of Illinois. That is the Jardine Water Purification Plant, right next door. So everyone's walking past it, they don't even know that it's sitting there. But this guy is the source of most of the water we use in Chicago, and including some of the places outside of Chicago. And the way it works is you can just see in the distance this little thing out on the lake. That's called a crib. There are 4 of them dotted down the lakefront. And what those cribs do, they're sitting in, 50 feet or so of water. They intake massive amounts of water. They're out offshore because the water's cleaner out there. And it goes down into a tunnel in the bedrock under the lake, and it flows from there to tanks here at the Jardine Water Plant, and it gets cleaned up. And then it's distributed to pumping stations and goes into homes and businesses all over the city. So that's the largest water purification plant in the world. You guys have any guess where the second largest water purification plant in the world is? We have that one too. It's down on the south side. The South Purification Plant is the second largest one in the world. So we work big here. So that gives us our water that comes into our homes that we use every day. And then we flush our toilets and dump water down the drains and whatever, and it's all dirty. And from there, it has to be cleaned up. And it goes to actually the largest wastewater treatment plant in the world, the Stickney plant. Not too far from here, pictured here from the air. And then it goes back into the Chicago River system, basically. So we're not dumping raw sewage anymore down the river to St. Louis. Now, if you live in Chicagoland, you're familiar with another challenge we have with water here. We have what's called a combined sewer. What that means is that the sewer lines which carry our wastewater are the same sewer lines that carry storm water when there's a big rainfall event. And all of that water goes to that wastewater treatment plant and a few other wastewater treatment plants. So when there's a huge rain event, a massive storm, all that water's got to go to that plant, and it can't handle that much water that fast. It's too much, even being the largest plant in the world. And what that means is the system backs up. And the place it backs up is into people's basements. And so if you live in Chicago and you've lived here for a while, you've probably had untreated sewage in your basement more than once, which is not pleasant, in case you've never experienced that. So the taxpayers of Chicago have not been happy about that, and so eventually this plan was put in place. It's known locally as the Deep Tunnel Project, but the official name is the Tunnel and Reservoir Plan Project. And the idea here is that there are massive tunnels that have been built under Chicagoland. They look like this inside. To give you a sense for the scale, that's a person. There's another person. That is a big tunnel. And the idea is that when you have a huge rain event and all that water comes in too fast, it goes into those tunnels. And then the tunnels, instead of emptying out into the wastewater treatment plant, they empty out into places like this. This is Thornton Quarry. Again, look at the scale. That's a truck right there. That's a big quarry, a big reservoir. It's actually the largest such reservoir in the world. And so that water comes rushing in there, fills up those reservoirs, and then it'll slowly work its way through that treatment plant at a pace that the plant can handle and ultimately clean it up instead of coming up in people's basements. So this whole plan is still underway. It's almost completed. I forget what the date is for completion, but it's maybe next year or the year after, something like that. So that will hopefully permanently solve the raw sewage in your basement problem. So we clean up the water in these wastewater treatment plants, then we put it back in the Chicago River. It is not perfectly clean. And I do not recommend that anyone today go out and take a swim in the Chicago River. It would not be the safest of places to take a swim. But the city of Chicago has long recognized the economic potential, tourism and otherwise, of that river, and they want to clean it up. And to their credit of the Metropolitan Water Reclamation District and the city, they are working very hard on doing that. In fact, they have built the largest UV disinfection plant in the world. That's the O'Brien plant, which empties into the Chicago River, and pathogen counts in the Chicago River have been going down quite significantly, and will continue to do so more going into the future. Places like Argonne, we're trying to do that. So the general strategy we have at Argonne with water is to first do a sophisticated analysis of the problem, data modeling and analysis, looking at where are the impacts, where are the water needs, what are the waste products here and the water needs over there, and so on. Sort of the big data analytics side, and identify where are the biggest challenges, where there could be technological improvements. If you could provide me a technology that did X using this much energy, that would solve this problem. That comes from the analysis side, and that feeds an effort in materials for water. Argonne's really good at developing novel materials for important applications. The battery technologies developed at Argonne are today in the Chevy Volt, in those lithium-ion batteries. So the idea is to apply that type of expertise to this problem of water. So I'll pick out a couple examples of the kind of things we're looking at. One would be groundwater dating. I mentioned there's all this water, 30% of the fresh water is down in those aquifers. And I said some are fossil water, some are renewable water. How do you know how old that water is? How long has it been sitting there? You can't use carbon dating because the half-life is too short. Well, it turns out that some folks at Argonne have been using radiocrypton dating, much longer half-life. Now, there's not a lot of radiocrypton in water. So what you need is a technique that can detect tiny little amounts of it, and they developed something called atom trap trace analysis, where they can quantitatively measure those tiny amounts of radiocrypton and tell you how old is that water. And so they've had pilot projects working, for example, with people at the University of Chicago and Ben Gurion University in Israel, where they've sampled a number of the aquifers dotted down the Negev desert, and they can tell you, that aquifer is 150,000 years old, this one's 600,000 years old, and so on, which is invaluable information for the water managers in Israel to understand those resources and use them intelligently. We're also working hard. I told you membrane technology is where I think the future is in terms of water cleaning technologies, and we're doing a lot of work with new types of membranes, and also trying to clean up pollution from our water sources so that we can, in a sense, increase the volume of available water for our needs. So I mentioned, it's such a big challenge with water. We face other challenges as a society. We've got climate change, we've got massive income inequality, and so on. And these are all very serious, big challenges. I would argue it's a little hard to muster affection for something like the financial system. I don't know, maybe you guys have affection for the financial system. I don't. But our affection for water is something that we're born with. Water is so integral to our lives from the day that we're born that we all have this innate connection to water. I told you the invisibility of water was bad for us in water. I would argue this connection that we have with water is good for us and for water. So what I'd encourage you to do, I mentioned that water is invisible. It's hidden all around us in our food and in everything, basically. I would encourage you to start seeing water so that we can all much more responsibly use the most important material on Earth.
Well, very briefly, the California aqueduct is famous for moving lots and lots of water into LA, destroying Owens Valley, but do you see systems like that proliferating around the country?
Moving large amounts of water from one place to another.
Yeah, because we did that.
We take Colorado River water and we move it to California. You got to pump that over mountains, first of all. Going through a pipe itself has resistance, but you got to go over a mountain. Hoover Dam, that's a big dam. It produces a lot of electricity. 1/4, actually more than 1/4 of the electricity coming out of that dam is powering that water system that's moving that water from there to California. It is enormously energy intensive. And the agriculture needs in California were deemed worthy of that expense. That's actually going to be a challenge coming forward. You'll probably hear about it in the news next year. The contract that was put in place to give them access to that electricity expires next year. And odds are that when they renegotiate that contract, they're not going to be able to get as much power from Hoover Dam as they used to because there are other folks who want that power. That means the price is going to go up for that water, which means in California they're going to be paying probably even more for water than they are today.
But what about in the Midwest, pumping water from the Great Lakes, where you don't have a lot of mountains? In fact, I find this place kind of boring because of your lack of mountains.
Yeah. So yeah, you don't have the gravity problem so much, but you have resistance when you go through pipes. And so that takes massive amounts of energy. And when you're talking about the volumes involved and you do the math on the energy, it's a lot of energy. And we also have an energy crisis. So where are you going to get that energy from? We don't have enough energy as it is. So yeah, we may have to start looking on maybe a regional scale, not like moving it to the other side of the country. We may have to start looking at some of that. You now have a new problem also if you're moving massive amounts of water from one basin to another, which can have long-term effects on the entire ecosystem in that basin, and that needs to be considered very seriously before you make such a move.
What role do you see for water recycling in addressing?
Yeah, so water recycling, as in using wastewater and turning it back into water in your home, we have no choice but to do that. And some people don't realize some of that's already happening even in the United States. Orange County has a system, for example. And there are other places where it's done on a pretty large scale. And that water is perfectly safe. As I told you, it doesn't matter what you put in water, you can get it out. But there is a psychological barrier associated with that. And there have been efforts, a famous one happened in Australia. They had what they call the Big Dry, this massive drought in Australia that ended a couple years ago now. But it was like a decade or more long drought, really catastrophic. Their reservoirs were like, gone in some cases. And so they started, of course, looking at water recycling. And then there was this massive upswell of public opposition to it, and they used phrases like toilet to tap. And do you really want to, that sort of puts the wrong picture in your head when you think about opening your tap. And it didn't happen. They ended up moving water at great expense from like another town to the town where they were going to do that instead. Cost way more than it would have to recycle the water. So yes, we need to do much more of that, to take dirty water, whether it's wastewater or other, and clean it up and reuse it rather than trying to tap into some new source, because there just aren't very many new sources out there. There is a whole social science, social psychology aspect to that needs to be solved, and I am far from an expert on that subject, but you're right that it is an important source.
But it seems the scope of the problem that we're having, it seems like water recycling to me wouldn't play a very significant role. Can you speak to that?
So we recycle almost none of our water right now. And we use a lot of water. So if we started recycling it, that would have a huge impact if we did it on a large scale. But yeah, it would have to be a really, really large scale. All those wastewater treatment plants that just dump back out, somewhere else need to clean up the water a little bit more and, feed it back into, a useful water distribution system. So yeah, enormous investment required to do that. But it could make a huge difference in our effective water supply, absolutely.
So the natural recycling for the fresh water that goes on, the runoff water, that depends strongly on the climate change.
Yeah.
So, and the droughts too. So
Yeah, I was not trying to decouple them, I was trying to couple them.
Oh, okay.
Maybe I wasn't clear enough. So,
Sorry.
yeah, droughts are getting worse because of climate change, which is making the water problem worse. So that's one way in which they're coupled. You're also right that precipitation patterns are also changing. So what's generally happening is we're getting more extreme precipitation events where a lot of water comes down all at once, and that's worse from a water standpoint because most of it just runs off quickly down back into the oceans, and you can't actually use it for things like agriculture and whatever. Like the monsoons in Southeast Asia are getting worse. Yeah. And so that's a big problem. I'll give you another one. Sea level is rising because of a warming planet. That salt water is starting to intrude in freshwater aquifers that are in coastal regions. So some of the fresh water that we've been relying on is actually now becoming salt water. And so that's another diminishing supply attached to climate change.
All water is local, isn't it? But not all economics is local, right? So other aspects of economics that you said, like a car and these things are being transported. So including if we add both, then it seems like the water problem is not completely local.
True, yeah, that's right. You can effectively move water by moving goods, right, in the way that I was describing. Now that doesn't help you for drinking or cooking or bathing, but it does help you in the water that would have gone into making, you don't need water to make a car in Algeria if you can import a car from somewhere else, and maybe you can use your precious water resources for drinking and cooking and those other things that are not replaceable. Yeah, so that, in a sense, alleviates some of this problem, and that's how we've been able to populate the Earth in the way we have, in part, is by moving virtual water around that way.
Just one more.
So why can't we have a cost model for water like we have for gasoline?
Why can't it be, the cost and the price be rational? Yeah, it's a great point, and again, I'm not an expert on this. I'm far from an economist or an expert on financial calculations, but I do know that water is not priced really in any rational way in most of the world. One exception to this is the country of Israel, I've been told, although I've not checked into this myself, that they actually do the math, calculate what it is costing them to desalinate that water. That's where a lot of their water is coming from now. Some from the Jordan River, but they've massively increased their desalination plants. They know, how much energy went in and so on and so forth. They did the math, and they are supposedly charging customers in some kind of tiered scale the actual cost of that water. I've not looked into that to see if that's accurate, but this is what I've been told. Most of the world, that is not the case. We are almost all universally underpaying for water, which brings up another point which I didn't say earlier. So I argued that water is underpriced, and that leads to abuse and waste and so on, taking it for granted. But, so that means, okay, so then let's increase the price to reflect what it actually is worth. But you have to keep in mind that water is, in a sense, a human right. You can't price people out of water because you need water to live. That would be immoral, I believe. And so how do you do that? Well, you could use tiered pricing schemes where, the first X number of gallons you use every month in a home is very low cost. And then you jack it up really high when you go beyond that to cut down on the people who are abusing the resource. And another point, that there's another need for water that is not just you and me. The world around us needs water. The trees and fish and the whole world around us needs water. And so if we say, well, we as humans own all that water and we're going to put a price on it and fight over those resources, what's left? Who's paying? The buffalo can't pay you to use its water. And so you have to reserve some of the water that we have in the natural system to maintain the natural system around us, or we're all going to pay a very dear price in the end.